everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So we're going to be looking at stereoisomerism in alkenes, and we're going to explain the terms stereoisomers, EZ isomerism, and cis-trans isomerism. And then we're going to use the CIP priority rules to identify the E and Z stereoisomers. And lastly, we're going to determine possible EZ or cis-trans stereoisomers of an organic molecule given its structural formula. Now we're going to talk about stereoisomerism in alkenes. So there's three definitions we need to know. The first is that stereoisomers are compounds of the same structural formula but with a different arrangement in space. And then EZ isomerism is actually an example of a stereoisomerism. And this is because there's a restricted rotation about the double bond. And so we have two isomers where the two substituents, which must be different to each other, and which are not hydrogens, can either be on the same side or opposite sides. And the final definition is cis-trans isomerism, and this is a special case of EZ isomerism, in which two of the substituent groups attached to each carbon atom of the carbon-carbon group are the same. And so, for example, if we looked at butene, so we have 4 carbons and we have a double bond on the second carbon. So we have 3 hydrogens and then we have a CH3 on the end. So this can have 2 isomer forms. The first is, so this is butene. If we center around the carbon-carbon double bond, we have a hydrogen, a methyl group, another methyl group, and a hydrogen. And now what we do is we see the two substituent groups which aren't hydrogens, so these two here. And they're on opposite sides to each other, because if we divide this horizontally, they're on opposite sides, and so we call this E-butene. Whereas if we wrote it like this, so we had the carbon-carbon double bond, and we had CH3, and then another methyl group here, and hydrogen, and a hydrogen, this would be Z-butene. And that's because if we divide this along the middle, horizontally, then they are on the same side, and so we call it Z. And for the E-butene, we can also call this trans, because the two substituent groups are the same. And for Z, we can call this cis, because the two substituent groups are the same and they're on the same side, so we call it cis. So if they're on opposite sides, we call it E or trans if the substituent groups are the same. And if the groups are on the same side, we call it Z or cis if the groups are the same. We also need to know how to determine EZ stereoisomers from the given structural formula. So in this example, find possible EZ isomers of CH3CH, CH2CH3. So what we do first is we draw out the carbon-carbon double bond. It's always easier if we center around this. And so first you see that we have 2 hydrogens which are attached to the carbon, and then the other 2 groups which are attached are an ethyl and also a methyl. And so we can put those in. So we can put an ethyl here, for example, and then a hydrogen would go here, and then we can put a hydrogen here and a methyl here. And now we look at the substituent groups attached to carbons which aren't hydrogens, so this one and this one. And we see that they're on opposite sides, because if we divide this double bond horizontally, they're on opposite sides, and so we call this E, the isomer. And because there's 5 carbons in the main chain, this must be some kind of pentene, and we can see that we have the double bond where the second carbon is, so this is E-pentuene. And we can also get Z-pentuene, because if we draw it with the 2 substituent groups on the same side, so we have an ethyl group here and a methyl group here, and the 2 hydrogens at the bottom. If we divide this double bond now horizontally, these 2 substituent groups will be on the same side, and so we call this Z-pentuene. Now we're going to look at the CIP priority rules for naming alkenes. So the first rule is that we compare the atomic number of the atoms directly attached to each of this double bond, each side of the double bond, the atom of higher atomic number is given priority. So what we do is we divide up the alkene this way. And so now we compare within a side. So first we're comparing chlorine and hydrogen. And chlorine clearly has the highest atomic number. And so chlorine gets priority. So this gets priority. And then now looking at the other side, bromine has an atomic number of 79.9. And then for CH3, we have 3 plus 12, which is 15, and so bromine must take priority. And so to work out whether this is an E or a Z alkene, because there's 3 substituent groups which are attached, which aren't hydrogens, we take the chlorine and bromine because they take priority. And so this is an E isomer. Now this is actually 2-bromo 1-chloro propane, but that doesn't really matter. We're just looking at if it's an E or a Z isomer. And then the second rule is that if the atoms attached to the carbon of the double bond are the same, you will need to find the first point of difference. And at the first point of difference, the group which has the highest atomic number is given the highest priority. So again, we split the alkene down the middle. And first let's look at the left-hand side. So clearly the atomic number of CH3 is much bigger than hydrogen, and so this takes priority. And then now looking at the right-hand side, we see that the first thing that's attached to the carbon of the double bond is a carbon, and so that's the same. And so everything is the same until you get to the first point of difference, where we have chlorine and an oxygen. And so now we look at which one has the higher atomic number at this point. And so the atomic number of chlorine is 35.5, and the atomic number of oxygen is 16. So this CH2CH2Cl must take priority. And so this is a Z isomer because the 2 substituent groups that we're looking at, the ones which take priority, are on the same side. And so we call this a Z isomer. Now we're going to look at some questions. So for question 1, an organic compound A is shown below. Explain how the Kahn-Ingold Prelog CIP priority rules can be used to deduce the full IUPAC name of this compound. So what we need to remember is that the first step is to look at the atomic numbers. So we compare the atomic numbers. And this is only if the atom which is attached to the carbon are different. The carbon of the double bond. And we have that a higher atomic number gets priority. And then the second step is that if the 2 atoms are the same, then what we do is we find the point of difference. And then at the point of difference, we need to see which one has the higher atomic number. So the higher atomic number gets priority. And so now we have to look at naming this alkene. So we divide it up in the middle vertically. And first let's look at the right-hand side. So we can use rule 1 for the right-hand side because the two atoms attached to the carbon are different because we've got a hydrogen and a carbon. And so we can see that this CH2OH has a much higher atomic number than the hydrogen, and so that takes priority. So we have that CH2OH takes priority on the right-hand side using step 1. And then looking at the left-hand side, we can now apply our second rule because the two things attached to the carbons are both carbons, so they're the same. So we find the first point of difference. So the carbons are the same, and then we have two hydrogens, and then this one has another hydrogen, whereas the top ethyl has a carbon next, so this is next. But then in the methyl group, we have a hydrogen which is next, because if we get rid of two of these, we have one more left, and so we would have a hydrogen. And carbon has a much higher atomic number of 12 compared to hydrogen's 1. And so that means that the CH3CH2, so the ethyl group, takes priority for the left-hand side. And this is using step 2. Now, to name this molecule, we need to know that the OH takes priority over an alkene group. So if I draw it a bit differently, so we have CH3CH2. So the longest chain we have is this one here. This is the longest carbon chain, so we have CH3, CH2, and then a carbon with a double bond, and then CH2OH. And then I have a hydrogen here and a methyl group here. So this would be some kind of pentanol, but it's got double bond, so it'll be a pentenol. So it'll be pen, and then instead of tan, it'll be 10, and then ol. And then now we need to know that when we label the carbons, the OH will be the on the first carbon. And so we label it like this. We have 1, 2, 3, 4, 5. And so this would be 3-methyl pent 2-ene 1-ol. This would be the IUPAC name. And now we have to use Z or E. So looking back at our priority parts of this alkene, we have that this takes priority and this takes priority. And now we can see that they're on the same side, because when we divide it horizontally, they're on the same side. And so this means that this molecule is Z 3-methyl pent 2-ene 1-ol.